Okay, I think everybody's here that seems to be coming. So, um, any questions before we start? Today is going to be our last lecture. Then the next 2 days we'll do review.
Are you gonna make like the study guide like you did for the last exam?
Yeah, I'll do that. I'm still working on the exam, so I have to hopefully get all that done before tomorrow, and then I'll send it out to you probably before the. If I get it done tonight, I'll send it out tonight. If I get it done tomorrow, I'll send it out at least before the class anyway.
And then are we just gonna spend like 2 days reviewing?
Basically, unless we get done with one day on tomorrow and you're like, okay, that's enough. We just want to be on our own and then we don't have class Thursday. Kind of depends on how that goes.
Okay, thank you.
Huh? All right. Well, if there's no other questions, today is our last lecture. It's on section 4.7, which is looking at exponential and logarithmic models. So our first one we're looking at is exponential growth and decay. We've kind of looked at that before just on its own, but the model we're going to use is going to be y equals a sub 0 e to the kt. So a0 is going to be our initial value at time 0, and then our k is going to determine if it's growth or decay. If it's positive, we have the constant is going to be a growth constant, and if it's negative, we're going to have a decay constant, and then our t is just time. And so two examples of an exponential growth and decay curve looks like this. And here we have the plot of y equals 2 times e to the 3x, where the 3 is the k. And so then we have 1 over k comma 2 times e is going to be 1.02 is another point because that's our initial value. So it'll be 0 comma 2. And then our other point over here is negative 1 over 3 and then 2 over e. So these are just points that are on the curve. And the same thing goes here, except now we have the 3 and 2 kind of backwards and we have a decay constant here instead. And so that's kind of what it looks like again. And when you're doing these, most likely we're not going to actually plot points by hand and do that. We're going to actually just plug it into our calculator. And so we'll just plug this value in, plug it in and see what we get. And then if we need to find points on it, we'll go from there and kind of, okay, what do we need at time 0? Well, at time 0, we know it's 2. And then what about, 1 or 2 or 3? And we can plug all these in and get the extra points if we really need to do that. So one thing with dealing with these exponential curves is we need to talk about order of magnitude. So basically it's the power of 10. So when we express our number in scientific notation, so this would have a lot of more things. It's going to be 15 more places out here before we actually hit the decimal. This part here has order of magnitude 10 to the 15th. And so that's when we're going to be working with these. We'll do an example here in a little bit. We're going to look at one at say time t equals, I don't know, I think it's 12, and then the other one is t equals 24. And we have one order of magnitude here, we have another order of magnitude here, and then we can see the difference in order of magnitude. So it goes up by so many exponents, basically. So maybe we started at 10 to the 4th, and we go to 10 to the 7th. So this is 3 orders of magnitude higher. Okay, so it's going up by 3 orders of magnitude. And so that's what we're going to be working with, orders of magnitude. If it's talking about that, that's what we're going to do. And so, sometimes they'll say, okay, plot it on a line. And so maybe you have over here 10 to the minus 15. Here somewhere is like a 10 to the minus 6. And maybe way out here, we have a 10 to the second. And so we have different, you know, orders of magnitude, and you can plot it on a log. This is like a log plot. And so maybe, these are the 3 points you have, and then you can see kind of this one's the largest, this one's the smallest, and this one's kind of in the middle here. But these are the order of magnitude, say, as they go up. Now we have the characteristics of the exponential function. Again, whether it's, exponential growth or decay. So, k greater than 0, we have growth, k less than 0, we have a decay. And so what we have is it's one-to-one function. We can draw horizontal lines and it's going to be one-to-one. We have our horizontal asymptote in both cases. It's going to be y equals 0. Now our domain is going to go from negative infinity to positive infinity, no matter which one we're doing. So we're going to have the whole domain. Now our range, because our horizontal asymptote's y equals 0, it's just going to go from 0 to positive infinity. It's never going to touch that x-axis because we have that asymptote on the x-axis. We have an intercept, that's our initial point, so that's going to be the intercept 0, a sub 0. And then we have our increase and decrease. And then again, we also have, the different points. And so the points are kind of labeled here. And again, it's not necessary to kind of really remember these. These are if they say, find key points, we can actually just, plug those values in and get them. But we can also get them if we use our calculator, we can find those values as well. So it's not a necessity to find these, but that's how we can if it's required, as far as plot these three key points, and then you have to find those 3 points, and then we just take 1 over the k, and it's negative here, and it's 1 over k, it's positive here, and then we have the initial point divided by e, and here we have the initial point times e. And similarly here we have the same kind of thing. The higher one is the initial point times e, but here we have it's a negative 1 over k because it's decaying, so it's on the left side. And here we have the 1 over k, it's positive, kind of like we have on the right side, it's positive. And then we have a sub 0 over e, and that's kind of like what we have here, and it's just how it follows the curve there. So let's look at an actual example. And here what we have is a population of bacteria doubles every hour. If the culture started with 50 bacteria, graph the population as a function of time. So before we can actually graph this, because what I'm going to do is I'm going to graph it just with a calculator, so I don't have to actually try to hand draw this thing. What we're going to need to do is we're going to have to come up with a function that we can plug into our calculator to actually graph this. So what do we know? Well, we know that a sub 0 is equal to 50 because we started with 50 bacteria. So that's at time equals 0. So that's why the 0. And so what we can do is we can plug this into our formula. And if we go back, this is what we're going to plug it into here, the y equals a sub 0 e to the kt. And so when we do that, a0 is 50, so we'll have 50, and then we'll have e to the k times 1, because it's doubling every hour, and that's going to be equal to, now if we're doubling, if that's initial, double that is 100, okay? So to solve that, we'll divide by 50. So that's going to give us 2 equals e to the k, basically. Now, how do we solve for this? Well, we're going to take the ln of both sides. So then that power rule allows us to bring that down here, and we have ln of 2 is equal to k. And so that gives us our k that we need. Now that just gives us the k for here, so then we can plug in any value of t. And so if we say y equals 50, and then it's going to be e to the ln of 2 times t, or we could say, this is population, so maybe p of t, that's equal to our y. So we've kind of converted our y here to kind of a function notation, but when we plug it in a calculator, it's still going to be a y. And so this is something then that we can plot, because if we can plot a 0 here, and then that's 50, we plot a 1, then it's going to be 1 times that, and raised to the power for the e, and we can do that. But again, I'm just going to plug it into the calculator, and we can see what our graph looks like there. All right, so we had 50 times e, and it was raised to the ln of 2, and in parentheses times, and then we had it times x. It's supposed to be times t, but we have x for our calculator. And if we graph that, that's the graph we get. Now, if we trace, it puts it all the way out to 20, but let's go back and look, make sure our 0 point is where it's supposed to be. And so 0, 50, so that looks good. That's our initial value at time equals 0, so that looks good. And now what I want to do is kind of use the features of the calculator to kind of look at a couple times. That way we can kind of see orders of magnitude. So, well, let's say we want to look at 12 hours. So what we can do, once we have it in this trace mode, we can just type 12, hit enter, and it tells us at 12 hours, those 50 initial, I think they were bacteria, are now at 204,800. So it's grown quite substantially there. Now what about from 24 hours? So that's 12. So 24 hours, we just type 24, and we get, what is that? 838,860,800. So, it's exponentially just grown huge. And so those features of our calculator are going to help us do this. Now, what I want to do is I want to write those two as orders of magnitude. So the first one, we had 204800, and that's at t of 12 hours. And then at t of 24 hours, we had 838860800. And so if we convert this to our scientific notation, that's going to be 2.0, and maybe we can go out to 5. It doesn't matter how far we go out. And that's going to be times 10 to the 1, 2, 3, 4, 5. And this one's going to be 8.39 times 10, and that's going to be 1, 2, 3, 4, 5, 8. So here we have something on the order of magnitude of 10 to the 5th. Here we have something on the order of magnitude of 10 to the 8th. And so we've increased by 3 orders of magnitude. Okay. So that kind of helps us see, just going from 12 hours to 24 hours, it's increased by 3 orders of magnitude. So that's quite large, actually. Okay. So, it's a simple thing. All they really gave us was it started with 50 bacteria, it doubles every hour, and we just plugged everything in we knew. And we first got our K value, which then we could plug into here. This then is an equation we can plug into our calculator and graph. And, so we got the graph. It's, something like that. It's going up way fast. And then we could decide, maybe at 12, 24, and you could go on however high you want to go to see, how much greater it gets after, 36, maybe 48. And it's just going to keep going up by orders of magnitude. All right, so that's kind of doubling. What if we want to do half-lives? So that's kind of most common exponential decay models when you do a half-life, because it's usually with radioactive isotopes. And so for the rate of decay for a half-life, that's going to be K is equal to minus the ln of 2 over T, where T is going to be your time in years for the half-life. And so that'll give us our K constant. Then we can plug that back into, something like this. We'll have our initial value e to that K times the T, and we can solve it that way. So let's look at doing that with this example here with the plutonium. So it says the half-life of plutonium is 80 million years. Find the function that gives the amount of carbon-14, I don't know why they changed that to carbon-14, but remaining as a function of time. I just copied this actually out of the book, so I didn't even read the whole thing as far as plutonium versus carbon-14, remaining as a function of time measured in years. And so what we're going to do is we're going to use this equation. K is equal to minus the ln of 2 over the half-life, 80 million years. And if we plug that into our calculator, I'm just going to write down what it is. I'm not going to go over there and show you. You can type in this pretty easily. So that's going to give us a negative 8.664 times 10 to the minus 9. Okay. So that's our constant. And so what we can do is we can plug that back into our thing. And so if we're doing the amount remaining, so maybe we can say, I don't know, let's just call it f of x just for ease. That's going to be a sub 0, depending on how much we start with, because it didn't tell us how much we start with, e to the negative 8.664 times 10 to the minus 9. We'll just put that whole thing in parentheses, times our x, since we're using x, and that's going to be in years, but we're going to say x is years in this case. And so that would be our function then to give the amount of, well, plutonium. I don't know why, like I said, I just copied it out of the book. I didn't even read it. Plutonium 244 remaining in that many years. So if we had, given a value of time, we give an initial value, we could find out how much is remaining after X number of years or times. So that's going to be our function. Okay. Now here, there's also something with radiocarbon dating. Now this one is C14, so like I said, I don't know why the other one had that. But given the percentage of carbon-14 in an object, determine its age. And so what we're going to do, we can express the given percentage of carbon-14 as an equivalent decimal. So maybe they say there's 20%. And so you have to convert that to a decimal, so that would be 0.20. And then we substitute K in the equation T. So we plug it all in, and then that's what we get as far as what our T is. And so that's going to be the remaining, so that's what we plug in here. And so if we ever have problems where we're looking at carbon-14, I don't think there's very many that we actually have to do in the book even. And that's kind of the equation we're going to do. But what I'm going to do instead is I'm going to do another half-life kind of formula, but this time I'm going to have a beginning amount. I know the half-life, and I want to know how much time it's going to take until we only have 1 milligram out of that original 200 milligram cesium starting amount. Okay, and so what do we have to do? Well, I'm going to plug it back into our equation where we had the y equals a naught e to the k times the t. Okay. And so what do we have? Well, we know that if we have half-life, if we start with 200 milligrams, then half of that's going to be 100. And so that's going to be our first step. And e to the, now what we need to do is find our k value. And half-life is 30, so that's times 30. So this is what we know just from what's given up here. We have the T is half-life is 30 years. We know we start with this, and since we're dealing with half-life, we need half of 200, and so that's 100. And so that's our first step. Now what we need to do is use the rules of logs to solve for K. Well, first thing we have to do is divide both sides by 200. So that gives us 1/2 equals e to the k, or k times 30, or 30k, however you want to look at it. Now, how do we get rid of that? Well, again, we're going to take the log of both sides, and I'm just going to take the natural log because we have the e here. And so that means now this whole thing can go down in front. And remember, ln of e is just 1, so that's gone. So we have ln of 1/2 equals 30k. Solve for k, so we divide by 30. And so k is equal to ln of 1/2 over 30. Okay, so that's our constant that we need, because that is how we're going to rewrite this formula so we can look at it for any time and any amount. And when we do that, what we're going to do is we're just going to plug that into it. Now, we can do this two ways. We can leave it as the exact number, or if we needed to, and they said, take it out to 4 decimals, we could take that number out to 4 decimals. But I'm just going to leave it as an exact. Okay, so that means we're going to have the actual equation y equals 200 e to the ln of 1/2 all over 30 times t. Okay. Now, we want to know, when is it going to be with 1 milligram? And so that is what I'm going to plug in for y. So I'm going to have 1 equals 200 e to the ln of 1/2 over 30 times t. So now I do the same thing as I did over here, except instead of solving for k, now this time I'm solving for t. So I'll divide by 200. And so then I have 1 over 200 equals e to the ln of 1/2 over 30 times t. And again, take your ln of both sides. Then this whole piece up here comes down in front. The ln of e just goes away. It's just 1. And so then what I have is, now I'm probably going to run out of room, ln of 1 over 200 equals, and then we'll have ln of 1/2 over 30 times t. Now I'm just going to divide both sides by this ln of 1/2 over 30. Over 30. Divide that by ln of 1/2 over 30. And so that all cancels. And now I plug all that into my calculator. And I find out, when to get to the 1 milligram, it's going to be t is equal to 229.315 years. Okay, so that's how long it's going to take to go from 200 milligrams to 1 milligram. And so the question actually asks, will it take more or less than 230 years until it remains? Well, this is how long it takes, so it's going to take less than 230 years. Okay, and to be exact, it's going to take that many years. So, we this is the answer to the question, but this is why it's less than that. Okay. So
When do
again,
we use the t equals ln of r over the -0? When do we use that with that?
that's only when you're using carbon 14. And so it'll there's I think I saw maybe one problem on that, and it was like worked in the book, so I was like, well, I'm not going to work that one because it's already worked. And so I thought it'd be better to I'll give you what it kind of the lowdown of it is. You need that R, and the key is it'll give you a percent, and you have to convert it to a decimal. And so then you plug that in, and you can solve for T. But yeah, the only time you use that is with carbon 14, because this is a special ratio and everything, and they worked it out to a simple equation for us in the book, and so we don't have to worry about all these other little extraneous numbers that are tied into it, and so that will give us the T here. But the lot mostly what our book works with is with radioactive isotopes like cesium or uranium or plutonium or things like that. We don't worry about the carbon 14 as much, and so that one was like a one-off. But I was like, well, kind of to give you what you need on that one, I kind of put it in here, and then I did an example with uranium instead of actually doing the example, that they show in the book with the carbon 14.
Gotcha. Okay.
All right, so now we've talked about half lives, things like that, but we can also double your time. And this is the way we calculate double time. So sometimes we look for T, sometimes we look for K, and we can always do it. We can just, swap these for each other, because if you multiply by K and then divide by T, those interchange one another depending on what we need at what point in time. And then the whole key is it's a positive ln of 2 on the numerator. And when you had the half-life, it was a negative ln of 2 because we're decaying. And with this one, we're doubling time, so we're going up. So this is going to be with the t equals ln of 2 over k, and this was the t equals negative ln of 2 over k. So those are the differences. One's with growth, one's with decay, and a key is that one's got a negative on it. All right, so in this one, it shows about Moore's law, which is saying that they're going to double the number of transistors on a computer chip every 2 years. And so, but now it's saying that, well, growth is slowed to doubling time of approximately 3 years instead of 2 years. And what we're supposed to do is find the new function that takes the longer doubling time into account, which is that 3 years. Okay, so in this case, t is equal to 3. So what we need to do is find k. And well, like I said, all we have to do is swap those two around. And so k is equal to ln of 2 over, well, we know t, that's 3. Okay, so that's our k value. So our function, now it's the growth function, but again, I'm just going to plug it in as f. And now I'm going to remember to put a t here because we're doing time. And so that's going to be equal to, now depending on what our initial value is, it's going to be a naught e to the ln of 2 over 3 times t, because this is our k we just calculated. And then depending on what year we are away and also what our a naught is, then that's going to tell us where we're at as far as the time and the function, where we're at with the growth. So the key on that one was being able to swap those two, plug in the 3 for the t, get that rate constant, plug that into our typical, growth function here. And so all we had to do was plug that in, and then that gives us our growth function. Now, again, they don't tell us what a naught is, and they don't want to ask what is it in, t equals 20 years or whatever. And so we don't have to worry about either one of those. They just want the function looking like that as far as what it looks like. And again, a lot of times when you're doing these, putting it in the exact number is kind of the key. Sometimes they'll have you round it to 4 decimal places or 5 decimal places, and then go ahead and do that. You'll put in the whatever that is, that value. But for exactness, ln of 2 over 3 is more exact than rounding to some decimal place. And so I think that one is what we should be doing as far as most of the time. Put it as your ln of whatever you're doing, 2 or 3 or 4 over whatever the number is in the denominator. Maybe it's a decay and you have a half-life of 80 million years. So put 80 million years on the bottom, and then we have that. So I think exact numbers are better in a sense of writing equations, because first it's just easy to plug that into your calculator and it's not a hard thing. But writing out so many decimal places to make it look good is hard to make it look nice. All right, then we have another law, and this is Newton's law of cooling. So it says the temperature of an object T, so basically our temperature here, in surrounding air with the temperature S, so that's our surrounding air, will behave according to this formula. So we have A e to the kt plus Ts. And what do we know? Well, T, little t, is time. Our A here is the difference between the initial temperature of the object and its surrounding. And then this K up here is the constant. It's the continuous rate of cooling. And so how do we use this? Well, what we do is we set Ts equal to the y coordinate of the horizontal asymptote. Usually it's the ambient temperature, whatever your ambient temperature of the room is. Then we substitute given values into the function to find the parameters A and K. So maybe you plug in at time 0, the ball that you put into the room was 50 degrees or something. And so then you have that, your initial temperature of the room, maybe that was 70 degrees. And so then after that, you can solve this and figure out your A, because at time 0, T is 0. Well, e to the 0 is 1. And so what we'd have to do is take, the initial temperature of the ball minus the temperature of the room, and that's equal to A. So that gives us our first piece. And then what we do is we substitute some other value in. So they sometimes will give you a second value. After 1 hour, the temperature of the ball has risen from 50 degrees to 55 degrees. And so then you could plug in those new values, and then you can solve for your K. And then after that, you'll have a function you can use to substitute for any time as far as what is the temperature at time X or whatever it is. And so you can do that. And so what we're going to do is we're going to do an example of this. And so what we have is a pitcher of water at 40 degrees is Fahrenheit is placed into a 70-degree Fahrenheit room. 1 hour later, the temperature has risen to 45 degrees. How long will it take for the temperature to rise to 60 degrees? All right, so let's write everything down. So initial temp is equal to 40 degrees Fahrenheit. And so that gives us the point 040, because at time equals 0, it's 40 degrees. Now our room temperature, it was 70 degrees Fahrenheit. We know it's going to take 1 hour, so time in this case is going to be 1 hour, and that's going to be when we use the second one here, and that's going to be the second temperature, I guess you could say, was going to be 45, degrees goes higher than that. 45 degrees Fahrenheit. So at time equal 1 hour, it's 45 degrees. And then they want to know how long will it be till it raises to 60. So final temperature is 60 degrees Fahrenheit. All right, so that's everything we know. And so what we're going to do is we're going to plug this value into our formula. And again, remember it was T of S is equal to A E, can't write here, to the K times T plus our TS, okay? So at the T equals 0, so we're plugging 0 here, the Y is 40. So we have 40 equals A E to the K times 0 plus TS, well, that was the initial temperature of the room, which is 70, okay? Now, E to the 0 power, anything to the 0 power, is just 1, so that's 1. So that way has A plus 70 is equal to 40. So subtract 70. So negative 30 is equal to A. So that's going to be, quote, our initial value. And what it was it's the difference. And that's what we said over here. A is the difference between the initial temperature of the object and its surrounding. And so that's how we would find that. All right. So now what we have is a new one. We have this part. We know that T in 1 hour gives us a temperature of 45 degrees. So what we can do now is we plug our A as negative 30 in here. We plug in our new temperature 45. We plug in the T is equal to 1. And we already still have our 70 degrees here. And so then what we're looking for is what is our K. So let's plug all that in. So we'll have 45 is equal to a negative 30 e to the k times, again, this is time 1, plus 70. Okay. All right, so let's start going and unraveling all this to get to the k. So first we'd subtract 70. So those are gone. So here we have a negative 25 equals a negative 30 e to the k, because k times 1 is just k. Now let's get rid of the negative 30 by dividing both sides by it. So we have 25 over 30. I'm not going to reduce it, but you could reduce it to 5 over 6 equals, and then we have e to the k. Well, how do we get rid of that? Well, we take the ln, and so we'll take the ln here. That comes down. Well, ln of e is just 1, so we get k is equal to ln, and if we wanted to, that would be, again, you divide that out 5 and 6, and so it's 5 over 6. We can put the 5/6 at this point, okay? So that's going to be what our k is, and so that's what this is. So now we have an A, we have a K, we have the TS, and now what we can do is we can solve for that T for our final temperature that they want us to look at. So they want us to figure out, when is the final temperature 60 degrees Fahrenheit? Well, 60 equals negative 30 E. Now K is ln of 5 over 6. And then times T, then plus 70. Okay. So now what do? Well, we just do what we've been doing, and except this time we're solving for T, so we subtract 70. So minus 10 equals a minus 30 e to the ln of 5 over 6. And then times T. Now we divide by negative 30. Well, that becomes a positive 1/3. So we have 1/3 is equal to e to the ln of 5 over 6 times t. And we do like we've been doing. We take the ln of both sides. And so that then can come down in front. And so let's go over here now. So we have ln of 1/3 equals ln of 5/6 times t. And then ln of e just is 1. So divide that by the ln of 5 over 6. Divide that by the ln of 5 over 6. So that's gone, and we get t equals, now we just plug this into our calculator, which is very easy. Just take ln of 1 over 3 divided by ln of 5 over 6. And what that gives us is t is equal to 6.026. And this is in hours. And so approximately 6 hours is going to take for that initial temperature picture of 40 degrees to rise to the temperature of 60 degrees, with the room temperature being 70, and finding our rate constant. When we went from the 40 to the 45, we got that rate constant, and so based on that and everything going to be continuous in that manner, then we have about the 6 hours is going to be how long it takes to get to that temperature. All right, so again, nothing super hard. You just have to kind of remember to put things in a proper order, and get to the point where you're going, and just kind of, it's slow, methodical, but it's really, if you look at it, it's a lot of repeated the same thing. We had it once here, once here, once here, and we just did all the same things, just solving for K and T different places depending on at what stage we were. Now, there's another model we can use here, and it's called the logistic growth model. So basically, these models approximately are exponential at the beginning, but what happens is we're going to hit this ceiling here, and the ceiling is the upper bound. And so that's the carrying capacity of whatever this model is talking about, whether it's carrying capacity of, a group of animals, how many can live in a certain area, or something. And so it'll get to a close to that, but it'll never reach that point. And so that's what the curve is going to look like. This is the function we're going to be using. And so that's what we have right here. And it's c over 1 plus a e to the negative bx. And the key things are c over 1 plus a is our initial value, okay? C is our carrying capacity, or the limiting, value. So that's where we have our horizontal asymptote here. And then B is a constant determined by the rate of growth. So depending on your growth rate, that's what your B is. And a lot of times what's going to happen is we might have some kind of initial value. We know maybe, we initially had 20 animals in this area, and so that's our initial value. And we know the carrying capacity maybe is, 1,000 animals. And so what we can do is then we can solve for what A is by setting that initial value equal to the 1,000 animals divided by 1 plus A, and then after that, we have to solve for A. So then we just do algebra and we can solve for A. And then after that, a lot of times they'll give us the B value if we have to. So we don't usually have to solve for B, but if we have to, we just have to plug in values off of our curve into it and solve from there. But what I'm going to show you on how we do it is we're going to look at one where we get the value, and it's kind of one that's kind of about the same as what we have now. It's influenza instead of the coronavirus, but it says an influenza epidemic spreads throughout a population rapidly at a rate that depends on two factors. The more people who have the flu, the more rapidly it spreads, and also the more uninfected people there are, the more rapidly it spreads. So these two factors make the logistic model a good one to study for the spread of communicable diseases. So obviously there's a maximum number of people that can be infected. That's your whole population. So, that's the most. And so in our example, it has at time equals 0, there's one person in a community of 1,000. So that's our carrying capacity. That's our initial value. That's at time 0 of the people who have the flu. So in that community, at most 1,000 people can get the flu. Researchers find that this particular strain of the flu, the logistic growth constant is, and they give us our logistic growth constant. And what they want us to do is estimate the number of people in this community who will have this flu after 10 days, and then predict how many people in this community will have this flu on day 15. And so we have two numbers we're going to look for. But first, we actually have to get an equation. And so if you remember, the C over 1 plus A, that was your initial value. So we know the carrying capacity, which is C. We know the initial value, and so we can find A. So that was going to be 1,000 over 1 plus A is equal to 1. Okay. Now we just have to multiply by 1 plus A on both sides, and we get 1,000 equals 1 plus A, because what we want to do is get rid of it. And 1 times anything is just itself. Now to solve for A, well, we just subtract 1 and we get A is equal to 999. Okay, so that's our A. We have our B over here. And so what we can do now is we can write, and I'm going to do this on the next page, we can write our function. So our function, and based on time, is going to be equal to, again, we have a carrying capacity divided by 1 plus A, which we found, 999, times e to the minus, and remember they said B was 0.6030, and then it was times t. So depending on what time we're looking at. So that's what we need to look at. So that is the first step. We need to find what that is. Now, what they said was find what is f of 10 and what is f of 15. Okay. Well, with 10, we're going to take 1,000 over 1 plus 999, and then e to the minus 0.603, and then I'm just going to drop that last zero times 10, and then the second one is going to be 1,000 over 1 plus 999 e to the minus 0.603 times 15. Okay. So let's go to our calculator and make sure we're going to type this in right. All right, so quit that. So now what we had was 1,000 divided by, now we need parentheses down here. We'll have 1 plus a, which was 999, times e. Now it's raised to the power, so now we have a negative 0.603. And then the first one was times 10. Now don't forget to arrow down so we have the parenthesis on the same level, and then another parenthesis. And so that's going to be 293.85. So I'll write that down, equals 293.85. So that's going to be roughly 294 people. Now, the nice thing about our calculators, we can hit second enter, and only thing we're changing is that 10, and we're going to 15. And now, 5 days later, it went from 293 people to 894.56. So F of 15 then was 894.565, which is approximately 895 people. Okay. So going back to here, this is going to be approximately equal to 294 people, and this one's approximately 895 people. So again, it does spread very quickly, as we can see, and the exponential in growth, it went from 294 to 895 just in those 5 days. Okay. So that's a good example. It kind of hits home for where we are right now, and I guess they probably are not taking into consideration social distancing here and things like that, because that really would slow it down a lot. All right. So the next one says, now we're kind of having to decide things if they're going to be linear models, exponential models, logarithmic models, and then after that we actually have to determine, what model it is and how to actually calculate the model. So this is another nice feature of our calculator. We can plug these in and tell it to plot it, and then we can look at the general plot, and from that general plot we can decide, is it linear, is it exponential, or is it logarithmic? So let's look at this, and I have to admit I cheated because it's going to take a long time to type all those in, so I put all of them in already. So those are the data points, and what we need to do to actually plot those on the graph, because right now what our graph is this, so we'll clear that out. And what I want to do is I want to plot it on here. Well, the only way you can plot points is hit second stat plot. So we have to turn on the stat plot. And so you hit enter once you get to the plot one. And I want to turn it on, so I hit enter again. And then I can say graph. And so now we can see the graph. Now maybe we should make our window a little bit different here. So let's go down. Maybe a max of, I don't know, let's put 400 instead of that. And maybe this could be 100. And it's still not, we can go lower if we wanted to. But what we can see here is we kind of have this exponential plot. It's going up exponentially. And so that's what kind of function it is. And so what we can say over here is, ask which is the one it is. Well, it's exponential in flavor. So that's the one it is. And now they say find the model. Well, finding the model is, I'm going to use two data points. I'm going to use the first one, and I'm going to use the last one, because it always is best to do a model using the ones that are furthest apart. So those are the two that I'm going to use. And remember, when we have an exponential, it's going to be something of the form y equals a0 e to the k times x. So that's kind of the model we're going to be using here. And now we're going to have our xy, and we're going to have two equations, and then we'll have to have two unknowns we're going to solve for, and we're going to work our way through it. So our first point is going to give us the equation 3.297 from here equals a naught e to the, and now we have 1 times k. And our second equation is going to give us 180.034 equals a naught e to, now we have 9 as what our x is, k. So now we've got two equations, two unknowns. Well, what I'm going to do is I'm going to solve the first one here for a naught, because then I can take it and plug it in here. And after that, I'll have two things with k in them, because this will have a k in it, and that'll have a k in it. And hopefully it'll work out so we can solve nicely that way. So if I solve that for a naught, how do I do that? Well, I'm going to divide both sides by e to the k. So that gives me 3.297 over e to the k. So that is what e naught or a naught is. Now I'm going to plug that into here now. So that gives me 180.034 equals, now I plug that in, 3.297 over e to the k times e to the 9k. Okay. Well, I've got numbers here and here, and I've got e to the k's here and here. So what I'm going to do is I'm going to think about this by first getting rid of this 3.297. So I'm going to divide both sides by that. So I'm just going to take times 1 over 3.297, and that's the same thing as divided by 3.297. So that cancels that. Now, if I think about this, what that is e to the 9k over e to the 1k. Well, we have same bases. Basically, those are the same. So we can take the numerator minus the denominator. And when we do that, 9k minus 1k is 8k. And so what we have is 180.034 over 3.297 equals e to the 8k. And again, we just took and subtracted those, and we got 8k. Now, how do we get rid of that exponent? Well, we take the ln of both sides. That then comes down in front. And so we have the ln of 180.034 over 3.297. Let's go ahead and put all that in parentheses so we don't forget. And that's equal to 8k, because ln of e is just 1. Now we divide that whole thing by 8. And so that is what k is equal to. So k equals ln of 180.034 over 3.297 divided by 8. Okay, so that's what k is. All right, so now what are we going to do? Well, now what we do is I'm going to go ahead and figure out what that is. So I'm going to, let's do that in my calculator here, because I think I don't want to keep writing that down. So let's go here, and that was ln of 180.034 divided by, and the other one was 3.297. And then that whole thing was divided by 8. And that's close enough to have to be a half for this problem. So a lot of times they're going to say just round to the nearest tenth or hundredth. In either case, those are still going to be both 0.5. So k is equal to 0.5. All right. Well, because of that, what we can do is now we know that if that's 0.5, we can find a naught. And so a naught is equal to 3.297 divided by e to the 0.5. Now we have to take that and solve it. So that was 3.297 divided by e to the 0.5. Oops, guess we didn't need that. Enter. And if we go again to 2 decimal places or even 1, that's just going to be 2.0. So that gives us 2. And so now we have everything we need to do to solve this equation. So then we can say f of x, or we can say y, or whatever we want to say, is equal to a naught to e to the k, which is 0.5 times x. And if we want, we can go ahead and put that in parentheses so we know it's the whole thing is raised to that power. And so that then is going to be the model of this set of data. So again, it wasn't hard. We just used 2 points, the first one and the last one, and worked our way through finding the things we needed to find. And luckily it simplifies down to something pretty easy, 0.5 and 2, and we get our final function there. Now, the nice thing is our calculator will do this as well, but we need to know some conversion factors. And so those conversion factors say that if we're given something in the form y equals a times b to the x, we can convert that to the form a sub 0 e to the kx. Well, remember, we had, a sub 0 e to the kx. But what happens is our calculator is going to give us something like that and not something like this. And so we need to find out how to get from the calculator to this later one, which is what we need. So what we're going to do is we're going to write our initial y equals a b to the x as y equals a times e to the ln of b raised to the power x. Now we know that ln of b to the x, we can bring that x down in front. And so then we have this function. Now we can write this as ln of b times x or x times ln of b, either way. And then if we do switch it to this latter, ln of b then is equal to what? Well, that's equal to k. And then a naught and a, well, those look to be the same. And so saying a equals a naught and k equals ln of b, we can go from what the calculator gives us to what we need it to be looking like here. And so what we're going to do is we're going to use the exact same data and see what the calculator gives us. So again, we already know it's exponential. And so that means we're going to have to use an exponential function to exponential regression to do that. So let's go to our calculator. Again, make sure we have all our data in here. That's our data. And what we're going to do is we're going to click Stat again. We're going to go to Calc, and we're going to look for exponential regression. So we go down, and it should be 0, exponential regression. We hit Enter, and L1 and L2 are X and Y's, and then calculate. Now this is going to be the key here. So A is going to be basically 2, and B is 1.648732261. And so that's the key, because if you remember, it was e to the 1/2 x, and we have something different here. So let's go back and write that down. What we have is y equals 2 times 1.6489 and so on to the x, and that's from the calculator. So that's what our regression analysis told me. But we want it in the exponential form like this. And so what we have to do is we have to use this change to get to there. And so when we do that, we're going to get y equals 2e to the ln of the whole thing, 1.6489, and then times x. And if we use all the decimal places, actually, when we take the ln of that, what we get is 2e to the 0.5x. Okay, and so again, with the rounding, it might not give us exactly the 0.5, but if we used all the decimal places we saw in that equation as far as when it gave it out the regression analysis, if we wrote all those down, put that in here, took the log of it, we're going to get back to that 0.5 times the x here for our exponential. And so that's in the formula. And if we look back here, that's what we got here. And this one, we did longhand. This one, it was pretty short because the calculator gave us this. All we had to do was take the ln of b, and we got our value here, and we had our answer. Okay, so those are 2 ways to get from a set of data to an exponential function, and that's usually the case is what we're going to be using as exponential functions. And so that's how we're going to get to there from our original set of data. Now, if we had to do if we found it was linear function, well, that's just y equals mx plus b. So then we just have to find our slope and the intercept, and we can get that pretty easily. So that's another way we can do that, because we have the y minus y1 equals m times x minus x1. So we can use any point, and the slope, 2 points will give us a slope, and then we can solve for the y equals mx plus b, which is also what actually our calculator will spit out directly, so we don't have to worry about that. And our calculator should spit out the logarithmic one as well nicely, but the exponential one, it doesn't. It gives it into the b to the x form, and we need an e to the x. All right, so where are we at for time here? We're over time. So what I'll do is I'll do one more example on, well, actually 6 more examples on an extra video to kind of show you how we can go from, this given function and solve all these things. And I'll put that up as well in a little while. So hopefully that helps. And again, I'll send out the exam test practice, whatever, either tonight or tomorrow, depending on when I get it done. And then for the next 2 days, we can practice.